Hey, welcome to Build 2, where you get to find out all the little background information for those people that want to see it. So this is the knife throwing machine video. This is the background on how this thing was built. So this started back in December is when I first started ordering parts for this, and it's getting released in August. So 8 months, I guess, of process of working on this while, overlap doing this and other videos. But really, it started in a spreadsheet. And that spreadsheet was just calculations, basically F equals MA of the force of throwing the knife and what is the mass of the knife and everything else that's going to travel with it. I knew the weight of the electromagnet that I started with, and then I was guessing at the weight of the plastic and other hardware. Had to use the weight of the belts because you're moving not just, you're accelerating one side of the belt, but both sides of the belt up to the same velocity as the carriage, same velocity as the knife. And you may have noticed in the video, this is one of the knives. I had these are the two knives that I learned to throw when I was in high school, and they are too heavy. So through that spreadsheet of the F equals MA, the M is too big on these knives for these motors. I would have had to step up to an even bigger motor, and then how fast can they get up to 6,000 RPM? So these aren't even, you can't buy these anymore anyway in this particular size. Everything they have has holes in the handle. I guess some people like to put their finger on there for where to hold it each time, or maybe for different distances. But I had to go to a lighter knife just to get the thing to work. But that was fine. I actually like throwing these light little knives. They're kind of fun. What else? So yeah, started with a massive spreadsheet. And of course, part of that spreadsheet was the diameter, not of these are idler pulleys on this end, but the diameter of the drive pulley. So I was thinking I was going to use stepper motors, and I remember sort of the old timers that I was around saying, yeah, stepper motors are slow. And it's like, what do you mean they're slow? They spin really fast. Like, no, they don't. They lose torque. Even as you get them up to peak RPM, they lose torque really quick. And I found that out when I was doing the numbers that, okay, if the top RPM is 6,000 RPM, or actually the torque starts to drop off after 5,500 RPM on these motors. And I said, okay, so 5,500 RPM, how big of a pulley, what diameter do I need to be able to make the belt speed, or basically the knife speed, go at 10 meters per second? And I needed at least like 40 something millimeter, and to have a little bit of wiggle room, I ended up going like almost right at 50 millimeter for these. And then that said, okay, how much torque? So on the stepper motors, I just kept increasing that diameter because they can't go so fast. But I would increase that diameter, and all of a sudden with that huge, like a 4-inch whatever, here I am mixing metric and English, but a pulley that big would be required for a stepper motor to get a knife to go fast enough. But then once the pulley is that big, now you don't have any torque anymore to be able to actually accelerate it. So the load would have to be, the weight of the knife would have to be some little finger knife or something, just some tiny little spike. So it became clear the stepper motors were not going to do it, and I had to get these clear paths. And of course, the first place I heard about these clear path motors was Shane, Stuff Made Here, was using them on some of his projects, and said after using those, he would never go back to stepper motors. And yeah, I kind of I kind of agree. Now I want to get some of these and put them on my milling machine to speed it up, because yeah, they are impressive and very fun to work with. One of the first challenges that we ran into, I wanted to know if we could throw one of these stainless knives with a magnet. and I used one of those electromagnets, and I was able to pick up the knife no problem. And I was able to hold it with quite a bit of force. And I was like, this is great. And then I turned off the power supply that was powering the magnet, and the knife didn't let go. It stayed stuck. And then I thought, okay, so what happened was it was magnetizing the stainless, and it was grabbing back at the electromagnet. And so I thought, okay, I'll reverse the polarity on the magnet and push it away. And that didn't do anything. You could hear just like a little click. And I read into it that they talk about this magnetic hardness, found a research paper on it. And yeah, depending on the level of austenite in the stainless steel, depending on the alloy, you can magnetize it, and then if you want to demagnetize it, you have to give it AC, so you have to flip the polarity on the electromagnet back and forth. And I think in the paper they were doing like 4 hertz, so 4 times a second they were flipping it back and forth, if I remember. I had my son program we tried to make our own H-bridge motor controller, and we did get it to work, but it didn't work as good as just an off-the-shelf H-bridge motor controller. So we got this motor controller, and if you don't know, H-bridge is for being able to take just some DC motor and change, like on the window, powered windows on a car, to be able to make the window go up, and then when you want to roll the window down, you swap the polarity and the DC motor goes the opposite direction. It's just like that. It's just doing it with solid state hardware. And so off-the-shelf H-bridge motor controller, my son wrote a nice little program to be able to vary the hertz of how fast you were cycling, I guess, flipping the polarity on it, on the electromagnet. And then we also had it tapering down just in case we had to do that, which ended up not being necessary. But 20 hertz ended up being kind of the sweet spot to let go of the knife. So you could just hit a button, and when that 20 hertz back and forth, 20 times a second, changing the polarity on the magnet, it would just drop that knife just like that. And it's like, okay, great, we found it. But again, with the master spreadsheet, to be able to throw a knife, we have to go from here to there at, as fast as we can. We peak out at 10 meters per second in the middle, and means you need to slow down and stop. So the entire stroke from start to finish is less than 90 milliseconds. So how many of those per second? And then we need 20 hertz to be able to let go of the knife. Wasn't going to happen. It's just, it wasn't going to be able to let go fast enough. You'd still be, you'd have to start your cycles before you even took the thing off. So we realized that just wasn't going to work. And so we ended up going for the mild steel, and it didn't have the problem. You could just turn the power off to that electromagnet, and it would just drop the piece of mild steel. If it was heavy enough, it would drop it just fine. And the weight of one of these mild steel knives was no problem falling off of there. So let's talk about that for a second. We mentioned that we have this length here. That was the other part of that master spreadsheet, was how long does this thing need to be? And if we're accelerating from a dead stop and finishing at a dead stop, then our peak velocity is going to be somewhere in the middle. So we have to accelerate and let go right here. So we're really only getting whatever overall length we choose to go with. We only get half of that to do our acceleration, and then whatever time you need in the middle to let go, whatever that mechanism, whether it's a magnet or a solenoid, and then start decelerating and hopefully allow the knife to go on its merry way. So I knew that almost any motor I chose, if we just had a long enough, if I made a rail as long as my shop, no problem. Just accelerate the knife, just keep going faster and faster, and then let go. But I wanted to be able to pick it up. We want this thrower that you can just pick up and walk up to the target. So I had been picking up just items around the shop and decided if I could keep it around a meter long, or something under 4 feet, that I would be satisfied with that. And so that's what I did, is I plugged that into my spreadsheet as, okay, if it was a meter long, or something less than that, if the overall length was a meter and we got it down to 0.9 or something. And then I also wanted a dwell in the middle, because figuring that there is some time required for things to actuate, even if it's the electromagnet, that we would accelerate up to top speed and then have some period where there's no acceleration at all. We're just constant rotation, constant velocity forward, and that would minimize the forces, hopefully zero out the forces on the knife, and allow whatever it was to let go, and then we start slowing down. So that was one thing that I did anticipate from day one, was needing a dwell in the middle, and then it didn't really end up doing us any good. And it's probably just because of whatever slop in the mechanism. The belts, they're pretty stiff, but they've got some stretch in them. So during your acceleration, I think there was something like 40 pounds force on the tension on the belts. I'm trying to remember if that was just one belt or if that was across both belts, but it was a lot. And where it was only 10 pounds that was on the actual knife pushing it was all the other weight and everything that was requiring that 40 pounds. But yeah, as soon as we go from accelerating to constant velocity, you've got all that stretch that is now finding its way back, and it didn't seem to matter how long. We made that an adjustable factor in the program. Didn't seem to matter how long we made that. It wasn't helping. When the knives weren't sticking, they weren't sticking for other reasons, and that wasn't helping us. It ended up being that pocket. So we had cut, I think you saw in the video, we'd cut a nice little slot, and me thinking machinist and design, everything, I'll make this a nice fit. And no, that just exacerbated the problem. We had basically the knife would be getting accelerated, and I could tell the fingers to retract on that solenoid way early, and it didn't matter. I mean, it wouldn't release until it at least got to that midpoint, and you saw in the video a lot of times it wouldn't release until it got all the way to the end, come to a complete stop. Now the forces on the pins are just the weight of the knife, and it would sit there and fall. And that happened so many times until we figured out, hey, and I was focusing on the solenoid fingers, thinking, how do I change the geometry at the solenoid to get this to work? And then just like took a break and just kind of thought about it for a while and thought, wait a minute, I can start to manipulate the shape in the knife. And said, let's try opening up this pocket, and that will automatically, we're accelerating the knife along, have the fingers in that pocket, and it'll give something. It's not going to be a lot, but it probably gave us just enough give to compensate for the stretch in the belts, and that as everything starts to go to that constant speed in the middle, it gives enough of a break to the solenoid fingers to be able to retract. And that ultimately ended up working pretty well. Let's flip this thing around. All right, the microcontroller. How are we controlling this thing? Everything I've done prior to this project was using an Arduino, and Arduinos are great. They're simple, they're straightforward, they are slow. And I remember reading about people that were using a Teensy, and it's like, what is a Teensy? Or you hear about Beaglebone Black and all these other different controllers, and I didn't know why, because the Arduino was working fine for everything I was doing, because everything I was doing was slow. This thing, when I started doing with that master spreadsheet, I started looking at, okay, figured out the diameter of the pulley, and then going 5,500 RPM, almost 6,000 RPM, and a standard, you can set the steps per revolution for these motors. They're servo motors, but they are behaving, I bought a model that is configured to work like a stepper motor. And you can go into the configuration software from ClearPath and just pick the steps per revolution that you want. They like defaulted to 800, but I set them to 200 because that's a very common stepper motor, steps per revolution. And I had done the math and figured out that each step was less than a millimeter of belt travel. I was like, okay, that's probably going to be fine. And with 200 steps per revolution and going 5,500 RPM, it was something like 18,000 steps per second. And looking at, I just looked in the forums of running stepper motors and multiple stepper motors with an Arduino, and people were saying the best you could hope for was like 3,000 or 4,000. You had to go get the higher end. The more powerful Arduino is the DUE or DUE, or however you say it, DUE, and it was only capable of maybe 4,000 steps per second when you pull some tricks with your programming or something. It's like, okay, that is not going to work. And again, I think it was Shane, Stuff Made Here, seems to be using Teensies on his projects. I'm like, okay, he's smart. Let's see what he's doing. And look those up, and there people are saying, yeah, it is a way faster processor. It's like instead of 16 or 32 megahertz, it's like 600 megahertz. And people were talking about 200,000 steps per second or something that they were able to get out of those. And it's like, okay, that's going to be fine. Yeah, but the penalty now for using a Teensy, the reason you don't want to use a Teensy is that they are a lower voltage item. They run on 3.3 volts. So when everything else is kind of set up around 5 volts, now if you want to interface with a 5 volt world using a 3 volt controller, then you have to get what's called a level shifter. And yeah, I went and Amazoned the whatever. Well, let's see. We initially used the Adafruit level shifter, and it was working great for all the testing. And then when we tried to bolt this thing down and make it mobile, I was like, hey, I'll use these more compact ones from Amazon that were like Texas Instruments or whatever they were. And I should have listened to the reviews. People said these are not worth it. You're just going to be, some people got them to work, but most people were having problems with them. And I should have listened to them, because we ended up switching back over to the Adafruit, and it made a big difference. But I just burned so many days trying to troubleshoot what wasn't going right. But there is an issue, it seems, and I don't know if it's with the Teensy or what, but I found on the Teensy, there's a forum just for the Teensies, and there was someone on there showing that, in particular, one of the input ports is really sensitive to just capacitance or something, and there was a picture they made where just the Teensy on a breadboard, and they could put a 10 centimeter wire not going to anything, and just by bringing their finger in and touching that wire, it was able to trigger it. And the fix was setting it as an input pull-up, which you're supposed to do, and then they have some internal pull-up resistors, but adding an external pull-up resistor worked for everybody that seemed to be on that forum. It did not work for me in this case, and that's where we had this thing firing on its own. And it did it a couple of times when we were breadboarding it, but it really started doing it when we tried to bolt everything on this aluminum frame. And I tried grounding stuff, I tried a bunch of things, and it was not working. And I ended up putting I tried, what the heck, I put a diode on, and it was just the inputs for these buttons. You could get to the point, I had a wire, just a long wire, because yeah, the wire is going, one of the inputs for the fire button, going from here along the body down to the input, one of the inputs on the Teensy. And I think I was using the input that this person was having the most trouble with, but I switched to other inputs and that didn't fix it. I tried using a heavily shielded cable. That didn't fix it. I had the wire, at one point I had the wire just laying along the frame, and I would go touch it to the input, even though the input was set to pull, input pull up and had a pull up resistor on it. I could touch that resistor with just a empty wire connected to nothing, and it would trigger it to fire. So I fixed that by putting a diode on it. Doesn't make any sense, but I did it, and that made it work way, way better. I thought I had completely taken care of it, and then as we were getting close to the end of the project, it started to come up again where it was firing on its own, and that was some of those me here at the bench going, why are you doing this to me? Because I had done everything that I could find online, and I ended up putting a capacitor on there, a couple of way too big. They don't need to be this big. But I put capacitors on both the range and the fire button. Have not seen a problem again with that, with the input. So I don't know if it's because of this big aluminum frame, if it's something inherent to the teensy. Seems like most people don't seem to have that issue, and doing the input pull-up is fine. But boy, I seem to really have that issue with this project, and it made it rough. So batteries, yeah, it's interesting. The motors are mostly rated for continuous duty, and they'll have like a peak whatever, I think for maybe 1400 watts, and they'll say like 10 amps, and then the batteries are rated for, these batteries are supposed to be rated for 10 amps, but for short durations you can go higher than that. And you know, I was trying to keep this thing under 20 pounds, obviously didn't, and I picked some hoverboard batteries. This is an extra one that I got because I was having issues. And what does it say? Current less than or equal to 20 amps. Like, all right, so I've got two 10 amp motors, so it should be okay. And they are 36. They call them 36 volt batteries, but when you charge them, they charge up to 42. So I put these in series, and that gets 84 volts DC that can kick out at 20 amps. So this is dangerous, dangerous stuff. Now the motors, they tell you right on the ClearPath website that you can't get the performance without being at least 75 volts, and they have a maximum 90 volts. So charging up to maximum 84, like comes at 84.4 or something when it's completely topped out, stays under the 90 volt maximum and stays above the 75 volts required to get maximum performance out of these things. So yay, that's pretty cool. Oh, I wonder if that's why. Okay, I may be having a realization right on camera. So I was going to talk about this anyway. Towards the end of the project, we were getting this thing really starting to work, and I started having some weird faults where the one of the motors, usually just one of the ClearPath motors, would fault out. And it wasn't a, they're pretty good about giving you blink codes to tell you what happens. And it's, nope, there it is. Never mind. I see what it is now. The one of the motors slipped. So we were having a fault, and I can see, I'll show you a picture of this, or some video of this, that I timed. I put a little ink mark across the pulleys, and the lower one indeed slipped, and I just had a fault out there. We were kind of showing this off to some family tonight, and it was randomly not working or doing this fault thing. It still worked fine enough to throw a bunch of knives. It was great, but when I first turned it on, just like boom, the first time it failed. So it looks like it's, I was thinking it was batteries, which is why I bought an extra battery here, but it looks like it might be a mechanical thing. So the ClearPaths they just started faulting out all of a sudden with a bunch of firings, and I started hooking up the oscilloscope, and we could see these little spikes in there in the voltage when it happened, and that is here just making me wonder if, since these are already at 84 volts, and if it was enough of a spike to get up to 90, that maybe these guys would fault out. So I'm not going to say that that's completely it, because it would alternate between which motor was doing the fault, but I can see right in front of me that one of the motors actually slipped. So anyway, we are experiencing a couple little bugs here and there, but legitimately on the video, we did get the 10 throws in a row, back and forth. There was no fancy camera work going on there other than maybe just cutting out some dwell as I was looking at the knives to make sure they loaded properly, because I didn't want to hit the fire button or just hold it down and let them shoom, 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 you know, come out of there. Because yeah, this thing is very much powerful enough to destroy itself. Fabrication was, you can see that most of the really sturdy parts are made out of aluminum, just 6061 extrusions that then TIG welded some stuff together. I didn't even show the TIG welding going on that happened. And then the carriage, you can see there are a lot of 3D printed parts on here, and that was another thing. You know, the internet is a wonderful thing, and it's been awesome to take inspiration from other YouTubers, Mark Rober and Destin, seeing what they were able to do with the projects that they did. And it was like, I have so much fabrication experience and resources that I should be able to really make a difference and get some really cool videos out there. And then Shane, Stuff Made Here, comes along, and oh my gosh, that guy is so much better at programming and has so much more fabrication experience and resources than I do. It's like, man, but what a great inspiration. And say I'm a patron of his channel, and I get as much from him as I possibly can. Learning about the Teensy, learning about these clear paths, and then the Form 3 is a heck of a printer. I could not have done this project. Yeah, I could not have done this project without the Form 3. The parts, a lot of these parts, especially the carriage, it's just strong enough. It is the right strength to do that job. And the last video I released, I made a link and lifted my truck, or the back end of my truck. By the numbers, it could have lifted my entire truck, but I got so nervous, like, okay, I'm just going to lift the back off of the ground. So it makes very, very strong prints. They are just strong enough. I'd say the right strength for this carriage, because it's strong enough to do the job, but then when I screw something up, or a bug in the program or something, and we end up crashing this carriage somewhere, it doesn't destroy the rest of it. You know, it ends up being sort of a mechanical fuse of the 3D print, just, you know, breaking. And then, okay, yeah, it's going to be another 12 hours or maybe 20 hours to print all the parts that broke, but at least I get to go to sleep and let the printer do its job. So again, just a wonderful thing of the internet to have all these talented engineers and getting out there and putting these projects out that we can all watch and learn and grow from. It's a really cool time to be alive, to be able to benefit from that and participate in it. Accuracy. So this thing is pretty accurate. If you watch in the video when I was doing that near far, for some reason, I don't know why, that one of the knives on the near target went like substantially below where the laser was aiming, but the rest of them were really close. And so I have had some wandering point of aim with this thing for some reason. I don't know if it's some loose thing in the mount or if the laser itself, I mean, yeah, it's this cheapy, it's like literally one of the cheapest lasers I could find, green lasers I could find on Amazon. So it's probably the laser itself just internally, but it could easily be the 3D printed mount that's in there. I mean, I probably should go back and make a metal one and make it more robust. But yeah, I have, from day to day, I've seen the laser, the knives going to the left of the laser point and the knives going to the right of the laser point. But at one point I did have it where I sighted it in to where the laser and the knives, I mean, they're just dropping in on a circle like that big really consistently. And then once I did that, I realized, shoot, I have to hold this thing, and there is some recoil involved with it. So for those tests that you saw at the end of the big video, I was like bracing my leg against this handle to try to use my body to keep, so I wasn't just letting it sway with my hands. And that did seem to help for the accuracy, consistency of it, that it isn't just sitting there. And you can watch sort of in the slow-mo when it actually does a launch, that of course as soon as it starts to move, the laser will get pushed off of where it was, but then the knife will come up and stick pretty much where the laser was aiming, at least for the ones that was sighted in on. Let's see, one last thing, the homing. Boy, that was kind of a pain. I didn't know from the beginning, especially with a stepper motor configuration, and these motors do have position feedback internally to them, but in this stepper motor step and direction configuration, that like I bought these, you're just feeding it step and direction pulses of where to go. So every time you turn the thing on, and I'll turn it on right now, it's walking back, it's trying to home. I'll turn it off. The motors are waking up, and it's like they're blind. They don't know where they are. They can take so many steps in the dark from where they are. You know, if you woke up somewhere in a field in the dark and somebody said take 5 steps, you could take 5 steps, you just don't necessarily know where you're going. And so it's very common with CNC equipment and all kinds of equipment using especially stepper motors, that they will have homing switches at one end or somewhere in the middle, that when you turn it on, the motors will just go at some slow rate towards the homing switch. And we kind of lucked out on this. I knew we would have to deal with that. I didn't think we were going to deal with it during this project. I thought we would save it for a later video or something. And then as we were trying to get consistent, it really came down to the magazine, getting knives to come out of the magazine consistently. Every time we turned it on, I would just eyeball the carriage and the clocking of the fingers and just try to make them vertical and try to put it in roughly the same spot. And that just wasn't consistent enough. So I just said, okay, we've got to take a couple of days and get this thing, get a home switch set up on there properly. And so we did. We put this switch, micro switch on the back, and it came to me that, wait a minute, if we have one of the motors enabled and the other motor disabled, that the enabled one could overdrive and push well, even if the lower one, even if the other motor was not able to move, we could at least run the carriage, just run one motor, and it would, and say I'm just moving one belt, and it will move the carriage. But if the carriage were to come up against a stop, check it out, I'm just holding the carriage with my finger, and if I continue to run the belt, well, it spins it was a magnet, spins the solenoid. And so I put a notch on the, one notch on the diameter of the solenoid. And so what happens is we mounted this micro switch where this thing rolls back until it finds the micro switch. You get a little click. And then as soon as it gets the click, the controller, the way my son did the program, is that it goes ahead and slows down and starts going until as soon as the solenoid is rotating and the notch lines up with that switch, then the switch releases and it breaks the contact. And now, so in basically one operation of moving the motor, we're just the upper one is the one we chose. We're able to get both position and the orientation, the clocking of that solenoid. And it is so elegant, and it worked so well that as soon as we did that, you could just see that every time you powered it up, it would put the fingers of the solenoid in the same spot and the same clocking. So that way, if we wanted to adjust it slightly, which I think we're still going to come back and maybe tune it a little bit, that when you made an adjustment, it would hold. Like it would, you could see that so consistently. Probably because taking backlash out of it, that it's running it all the same direction, whereas I was just moving it and eyeballing it, and then we would turn the motors on. You could see it, everything would jerk a little bit when you turned it on. So this way, everything's already powered up, and it takes all the slop out in the same direction. It makes amazingly consistent, which made it so much easier to get this thing working and working well and throwing knives consistently. Anything else? This has been going on really long. Yeah, so if you have any ideas, the next video we're gonna do, we're gonna use this thing and probably even do some more refinements on it, but the video is gonna be just trick shots. We're just gonna have fun. It was so hard to make this thing. Man, it brought me to my knees. And I could have come up with the program on my own, but it made it so much easier to have a helper that could do, and he really did do all the programming, that I could just say, look, I need it to do this now, and get him in here and get him programming it, and he would do it. And it didn't always work the first time, but he'd figure it out. And by the way, that was probably the best part of this project, was giving that experience that you typically only get as an engineer, where you're facing problems and they're daunting, but you're working through it and developing a product or developing a process, whatever it is, and you just keep running into things, and it can get really discouraging and depressing, and yeah, it makes you want to pull your hair out. But for my son, I mean, my daughter saw some of it as well, to experience that with coaching from me, to get like, hey, look, yeah, we're gonna break stuff. I mean, there was a point we had broken had a big crash that I didn't get on camera, so I was really frustrated with that. And then we're concerned we were going to break it again. It's like, no, it's okay, and we're probably going to break it again. That's just, it's something new. And whenever you're doing brand new things, mistakes are going to happen. That's just, if mistakes aren't happening, you're not doing anything truly new. So yeah, to get that kind of coaching, to work through that as a team, that was really cool. That was probably the biggest benefit, and really the most long-term enjoyable thing for me, looking back on it. So yeah, the next video, we're going to be doing just total fun stuff of a really popular, style YouTube video of what can it do. As my son would say, we haven't stuck whatever it is about sticking watermelons or doing something with watermelons is such a big YouTube thing. So we'll try slicing stuff. We're going to do, okay, cut the cheese, here in the US is a euphemism for passing gas. And so we'll probably put a piece of cheese on there and range the target, and then step like a quarter of a turn forward, so that instead of the knife going point in, it'll actually chop. And so maybe we'll do some chopping steps with it or something. We're just going to have fun and see what we can do. So if you want to go into the comments and give us an idea of what kind of trick shot you think we could do, maybe we've got a wall that we throw the knife has to go over it and stick into something on the other side that we can't see. All kinds of cool stuff we could do. If you got any other questions, throw them in the comments. Actually, Discord, getting on the Quint Builds Discord server, if you really want to just ask me a question, that's the way to do it. Of course, there's a pay section on there that I'm going to be much quicker to respond to. There's already people on there, so join them and be part of a group of like-minded people that are curious about this kind of stuff. Thanks for watching. See you in the next video.